Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is basic electrical quantities. Our objective today is to introduce the basic electrical quantities of voltage, current, resistance, and power. We will discuss the units, common instrumentation used to measure them, and the means of calculating these quantities. Right up front, I want to clarify the title of this lecture, Basic Electrical Quantities. Realize I will discuss basic electrical quantities basically. I do not wish to get into unnecessary technical detail at this point. However, I do want to give you a worthy preview of common concepts that we'll deal with over and over throughout the course of the Basic Electronics series. As such, I will make broad sweeping generalizations, wholly inaccurate simplifications, nebulous analogies, and use comically contrived examples. I want this lecture to serve as a quick peek inside Pandora's box before we smash the box open and a fire-breathing, bat-winged, thousand-tentacled monster explodes out of it. As we delve deeper into this lecture series, I plan to show you more and more of this monster, a tentacle at a time when it's appropriate to do so. I do not wish your brain to explode in sheer horror. Yet. The time will come when you're ready to face the horror full on, but first you must sharpen your wits, learn a couple block check strike combinations, and show up to lab every day prepared to train for battle. This is an extremely important lecture, and it may take you some time to understand the information I'm trying to convey. I'm encouraging you to pause the lecture at any time and think about it. Really think about it before continuing. Draw pictures, take notes. As much as I'm denigrating the contents of this lecture as basic and contrived, I'm kind of embarrassed to admit I use these simplifications all the time. Yes, I know all the details about the chemical reactions internal to a lead-acid battery, the Lewis definitions of acids and bases, and the subatomic detail of electron orbitals, but when it comes down to it, I look at a battery and say, there's a black box with a wall inside. On one side of it is a bunch of negatively charged electrons. On the other side of it is a bunch of positive charges. The electrons want to get to that side, and I just call it good. When you hook an electrical load, like a motor or a light, from one side of the battery to the other, the electrons have to travel through the load to get to the other side, since they can't go through the impenetrable wall. It doesn't matter which model you use. The overly complicated and time-consuming internal chemical reactions of the battery as a source of charge imbalance, or the quick and dirty mental image of a crowd of rowdy electrons in a pub crawl looking to hook up with a hot proton. The result is the same, moving electrons through a device. Which brings us to the first two basic electrical quantities I like to discuss, namely voltage and current. Voltage is why charges move. Current is how many charges move in a given time period. Oh, one more ground rule before we continue. I want you to forget everything you know. Wait a second, stop. Don't forget everything you know, because I want you to be able to find your way home tonight. If you did forget everything you know, sorry. Look for a policeman or fireman to help. Actually, I want you to forget everything you know, or everything you think you know about electricity. I want you to forget about every electrically related event you've ever seen or heard in a stupid sci-fi movie, action movie, any movie with Arnold Schwarzenegger in it, Total Recall being the notable exception, and all those cheap and hokey simplifications peasants use to explain something they know nothing about. Forget about ground. You know nothing about ground. Electricity does not take the path of least resistance. Voltage does not flow. All right, breathe in, breathe out. You should be an empty vessel waiting to be filled with knowledge. Voltage appears across something. Current flows through something. The terms across and through don't mean the same things. Voltage and current aren't the same thing, and they aren't measured the same way. Think about the terms across and through. You go across a bridge. You go through a tunnel. Across means there are 2 points. A bridge connects one shore of the river to the other shore. There is a difference between them. The difference would not exist if there was just one point. Realize you don't have to cross the bridge though. You could swim across the river from one shore to the next. The bridge could be broken and spanning an impassable bottomless chasm. The difference still exists, despite there being a path or no path. Through means one point. The the tunnel goes through a rock wall. There is no other way around. Yes, there is an entry and exit to our tunnel, but you still have to go through this single tunnel to get to the other side. If the tunnel is collapsed, or the input or output not connected to something, there can be no flow through the tunnel. Through implies there must exist a path. Across versus through, despite being non-technical terms, is the fundamental difference between voltage and current. It speaks volumes about their nature and how to measure them. Before we bring charges and meters and units into the picture, let's use a very simple model to illustrate across versus through and find similarities in our simple model between the basic electrical quantities, voltage, a differential across something, and current, a flow through something. Here is a box. There is a quantity of red hot water on one side. There is a quantity of blue cold water on the other side. There is a wall between them. There is a difference in temperature and color across them. You can measure that difference using a 2-point measurement. The red side is hotter and redder or more positive with reference to the cold blue side. One could just as easily say the blue side is colder and bluer or more negative with reference to the red side. With reference to is an extremely important term to understand regarding voltage. With reference to means here's the point I'm comparing all other points to. With reference to your lab partner, you are smart and good looking. This is the person to have as your wingman when you're out on the town. You're going to get a lot more action when a potential mate is faced with the prospects of going home with you or going home with someone that smells like the reptile house at the zoo. With reference to also means it's relative in nature. With reference to your lab partner, you are a total catch. With reference to me, I mean, come on. You look and smell like one of those wrinkly naked mole rats. Now that I've crushed your fragile eggshell ego, let's talk about flow. With no passageway connecting the hot red side to the cold blue side, and giving the wall between them is impenetrable to flow, no flow exists between the two sides. That being said, the difference between them still exists. Now, hook a pipe from one side to the next with a water wheel inside the passage. If a difference exists, hot red molecules of water move this way. Cold blue molecules of water move that way as both sides diffuse towards balance. As these molecules move or flow, they do work by spinning the water wheel or motor. The water wheel is resisting or opposing the flow. If the water wheel wasn't there, we'd have an uncontrolled mixture or uncontrolled flow. If the flow is controlled, we can now measure the quantity of molecules that pass a single point in a given time. This single point flow rate measurement is equivalent to current. Current is the flow or movement of a physical particle, namely an electron, through something. In this model, I'm showing an equal and opposite movement of both red and blue particles, so you'd think they cancel out, but realize in an electrical system only one thing is moving, the electron, so there is a net movement in one direction. That's the problem with these simple models. They're only good to a certain point. As water molecules continue to flow from one side to the other, realize what is making them flow is two things. One, the passageway between them, and two, most importantly, the difference between the two sides. This differential is equivalent to voltage, and it is the reason why charges move or flow. Voltage causes current. Realize that differential in our closed system, if there is no other outside source continually striving to maintain the imbalance, is becoming less and less over time as red hot moves one way and cold blue moves the other. When all the water in our closed system is neither hot nor cold nor red nor blue, but rather a uniformly warm, uniformly purple color, we can say that there is no difference between the two terminals of our energy source, nor is there any flow exchange between them. We have effectively discharged our battery. Leaving these analogies behind, voltage is the reason why electrons or charges move in the first place. Voltage is the cause. This differential is measurable using the unit of volts, often abbreviated with a V, where a voltage measurement must necessarily be a 2-point measurement across something. Be aware you can use SI engineering prefixes to distinguish between different magnitudes of voltage. For example, 1,200 volts is also 1.2 kilovolts, and 0.035 volts is also 35 millivolts. The engineering prefixes just make it easier to write and read unusually large or small numbers. The moving charges, or current, is the effect. The measurement of current must necessarily include a complete path for electrons to flow, and must necessarily be a single point measurement somewhere in that path through which all moving electrons can flow through and be counted. The unit of current is the ampere, or an amp, abbreviated as an A. The same qualifiers exist regarding engineering units. 0.020 amps is 20 milliamperes. If voltage is the cause of current, then current is the effect of voltage. So now when some shoeless peasant tells you that it ain't the voltage that kills you, it's the current, you don't have to feel bad when you assail them with a heavy bamboo cane on both sides of their head, their collarbones, their elbows, their wrists, their ribs, and their knees, because after all, it's not you that's hitting them, it's the cane. If voltage is the cause of current, then current is the effect of voltage. If there is a large cause and little opposition, there will obviously be a large effect. If you reduce the cause and keep the opposition the same, you should obviously observe less effect. The quantity that limits, controls, or opposes current is our third basic electrical quantity, known as resistance. The unit of resistance is called the ohm, symbolized by this horseshoe-looking thing called the ohm. With a constant cause and more opposition, one will observe less effect. Same cause, less opposition, more effect. This extremely important cause, effect, and opposition relationship is known as Ohm's law. It is not that hard to learn, and it's going to be the most frequently used tool in your toolbox throughout the course of this entire basic, intermediate, and advanced, and super advanced electronics series. You are going to wear the handle off this tool, and eventually Ohm's law is going to be so ingrained in you that you won't even think of it anymore. It'll just be part of you. If you're missing this part of you, that tape they stretched across the finish line is not going to break across your chest at the end of the race. It's just going to stretch taut like a bowstring and fling you backwards to the starting line. I'll devote another entire lecture to the single topic of Ohm's law, so I want you to remain in a state of unblinking cat-like alertness until then. In the meantime, just think of the terms cause, effect, and opposition. If you know the cause and opposition, you can determine the effect by dividing cause by opposition. Or in this case, if we know the voltage and resistance, we can determine the current. If we can observe and measure the effect and the opposition, it's very easy to determine the cause, because it's effect times opposition. Or in our case, it would be voltage equals current times resistance. If we could observe and measure both the cause and effect, it's very easy to determine opposition, where opposition is equivalent to cause divided by effect, where in our case, resistance is equivalent to voltage divided by current. The terms make sense, and I have not even put any numbers in there. A brief note about the diagrams I'm going to use for pretty much all of these lectures. If I had to constantly draw accurate pictorial representations of batteries and meters and everything else in the toy box, we'd be here all day. Therefore, I'm going to start using schematic symbols. This quick and dirty symbolic method is a common shorthand means of drawing electrical circuits. Schematics are like writing a foreign language. At first, it's going to seem weird and unwieldy, but after a time, you get very adept at writing and reading schematics. Long story short, schematics save time, and once you learn how to read them, hint at the functionality and purpose of an electrical circuit. This is the schematic symbol for a battery or a DC voltage source. DC stands for direct current, and it means that the direction of induced current doesn't change. This is in contrast to an AC source, or alternating current source, that switches the direction of induced current at regular or cyclical intervals. Just ignore AC for now. Notice the schematic symbol for a DC voltage source has long lines interspaced by short lines. What this is supposed to represent is the plates of a traditional lead-acid battery. Notice the schematic symbol for the DC voltage source has a plus and minus on it. These are its polarity markers, meaning the terminal with a plus on it has a higher voltage on it with reference to or compared to the one with a negative terminal. Again, voltage is a two-point measurement. It would be just as easy to say that the terminal with a negative on it has less potential energy with reference to or compared to the positive terminal. My symbol for a voltmeter has a red and black lead. Sometimes you'll see a plus and minus on it if I'm using all one color to differentiate between the purposes of the two leads. The positive, customarily the red lead, is the high lead. The negative, customarily the black lead, is the one that is used as a reference. If you measure the voltage of an ideal 12-volt DC voltage source with your reference on the negative terminal of the battery, the positive terminal of the battery is 12 volts higher than the negative terminal, and your voltmeter will read plus 12 volts. If you switch the terminal used as a reference, meaning you place the voltmeter reference on the positive terminal and measure the negative terminal with respect to the positive, you find the voltmeter now reads negative 12 volts, as you'd expect. The magnitude of difference is the same, in both cases 12 volts. However, you just changed your reference position. Like I said, it's all relative, just like the dating scene in Clackamas County. The symbol I'm going to use for an ammeter, by the way, is the device used to measure current through something, is an A with a circle in it. An ammeter has an indoor, symbolized by the plus, and an outdoor, symbolized by the minus. The ammeter itself is a single point measurement, and current must flow through it. To measure current in an electrical circuit, the ammeter must be inserted into the circuit. Additionally, the circuit must have a load in it, or an opposition to the cause for current to be controlled. If the load wasn't in there, the current would be uncontrolled, and your ammeter would just start on fire, and you'd spend the rest of the day in the hospital getting your lab instructor's boot surgically extracted from your backside. More on current measurements later. Remember, for our ammeter, current must flow in the indoor and out the outdoor. If 2 amps of current enters the indoor, there's a little dude inside that ammeter. Seriously, there is, counting the quantity of electrons that pass by him in 1 second. If you accidentally swap the outdoor with the indoor and vice versa, and now 2 amps are entering the outdoor and leaving the indoor, the little dude inside the ammeter just think 2 amps are leaving and writes negative 2 amps on the ammeter screen. The take-home point is, notice current must flow through the ammeter. The magnitude's the same, it's just your reference is messed up. The take-home point is, notice current must flow through the ammeter. I would never, ever, ever hook up an ammeter like a voltmeter for 2 reasons. 1, because it's not a voltmeter. Current needs to be measured through something. And number 2, it's extremely stupid and dangerous to do so, because an ammeter represents a path of 0 opposition. You could potentially damage your equipment or yourself doing so. You will do this incorrectly 1 time. If you do it a second time, you'll be sitting in the iron chair for 2 minutes. This is not a cruel and unusual punishment. It's just plain cruel, and I usually do it. Now that we've discussed 3 basic electrical quantities, voltage, the cause of charge movement, current, the effect of voltage, and resistance, the opposition of charge movement, and common schematic symbols in sufficiently nebulous terms, let's briefly discuss the actual meters used to measure them. Obviously, a voltmeter measures voltage. An ammeter measures current because an amp is the SI unit of current. An ohm meter measures resistance because the ohm is the SI unit of resistance, and coincidentally, the sound of the universe. Carrying 3 separate meters that do 3 separate tasks would be kind of a pain. So quite like mixing a cobra, a beaver, and a duck together to make a platypus, you can combine all 3 of these meters together and more into something called a digital multimeter. The term digital multimeter is often abbreviated as DMM. This is your first slang term, and I'm encouraging you to use it often in the presence of your non-electrical technician friends and family. It makes it sound like you're really techy and smart, even if you know nothing beyond this abbreviation. The DMM is a single meter that has multiple, hence the term multi-mode settings. It has flexible leads that plug into holes on the meter. Typically the black lead goes into the black hole and the red lead goes into the red hole. You'd be surprised how many people mess this up under stress. The meter could be auto-ranging, meaning it picks the appropriate range for you, or manually ranged, meaning you must pick the appropriate range prior to measurement. Finally, and most importantly, you must know where the DMM goes, depending on the function, to make the measurement you're looking for. Voltmeters go across, ammeters go through. We'll set up the DMM using the same checklist every single time. I am not urging you to use this checklist every time. I'm demanding you use this checklist every time. The use of this checklist will save your measurement equipment and circuit a lot of costly downtime and may potentially save your life. I am not overstating the benefits of using this checklist. Use the checklist. Think about it. Really think about it. Take your time and think before you act. The checklist has 4 steps. Follow them 1 through 4 and you'll get it right every single time. Skip a step, do a step wrong, or do a step out of order, and you'll get it wrong every single time. Function. Choose the quantity you want to measure. Voltage, current, or resistance. There's a bunch of other modes. Just ignore these for now. We'll get to these later. Leads. Put your leads in the correct place. For voltmeter and ohmmeter mode, the leads go in one place. In ammeter mode, they go in a different place. Customarily, the red plug goes in the red hole and the black plug goes in the black hole. You can do it backwards, but that'd be pretty hard-headed. Range. Choose the appropriate range if your DMM is not auto-ranging. More on this later. Placement. This is the single most important step in our checklist. You must put the DMM in the correct place to take your measurement. Do anything different and you can't take the measurement you desire, or you'll damage the meter, your circuit, or yourself. To measure voltage, you must place your leads across the terminals of interest. To measure current, the current must flow through the ammeter. To measure resistance, the circuit must not be energized and the device must be removed from the circuit. More on resistance measurements later. The big takeaway from the checklist is that voltage is across and current is through. Realize I'm delivering the contents of the Basic Electricity and Electronics series from an algebraic and conventional current perspective. What this means is 2 things. Algebraic means I'm not using calculus. Calculus is a special type of math that explains rates of change in area using techniques called differentials and integrals. You don't necessarily need to use calculus to be an electrical engineering technician. So I'm using a level of math, algebra, easily attained by most people. I've done both methods before, and I actually prefer the algebraic means of teaching electricity and electronics. When time and occasion arise, I might hint at calculus in later lectures, especially when we get to AC, just to keep all the math nerds in the house entertained. However, for the most part, you can pretend calculus doesn't even exist, and just use the algebraic means I use to solve equations and understand electrical phenomenon. Speaking of electrical phenomenon, realize for the most part you can't see electricity, but only observe its effects and measure it numerically on a meter. It's for this reason I'm willing to forgive Ben Franklin for a major error he made in 1752 that has been carried forward into our modern era. Ben Franklin chose a direction he thought electrons were traveling, and that direction became the accepted convention, hence the term, for current flow from that point forward. He thought electrons went from the positive terminal of a voltage source to the negative terminal of the source. They didn't have Wikipedia in 1752, so no one could prove or disprove this assertion, and it wasn't until much later somebody actually looked it up and found out he was wrong. Regardless, every ammeter made from 1752 forward reads current as if it flows from positive to negative of a voltage source. Electrons, the actual moving negatively charged particles that flow through an electrical circuit, in reality move from the negative terminal to the positive terminal. This being said, who cares? If my ammeter reads 2 amps of conventional current going from the plus to the minus, and those 2 amps of current are being used to heat up a resistive coil inside a heating element to keep my house warm or move the shaft of a motor, do I really care that 2 amps of electrons are actually flowing the other way? It's still 2 amps. It's just that the accepted convention of flow is positive to negative, and that's the way your meter's going to read it. And that's how we're going to talk about it for the remainder of the Basic Electronics series, because that's the convention, meaning the accepted standard used by everybody. Now, realize it would not be a standard if there weren't organizations or textbooks or individuals that refused to accept this standard and try to do it their own way. Look at Quebec. If Canada says forward, Quebec says backward in a different language, just to be a jerk. You might enroll in the Navy NEETS course or pick up a textbook that uses electron flow theory, the opposite of conventional flow theory, and be all like, the fuck they talking about? My advice is relax. Electron flow theory is technically correct. It's just that no one uses it, and everyone uses the accepted convention that current flows from the positive terminal of a voltage source to the negative terminal of a voltage source. Even if you hook up an ammeter backwards and conventional current is going in the outdoor and out the indoor, the magnitude of the current is the same. The accepted polarity or sign indicated by the ammeter is always with reference to conventional current. Measuring current with an ammeter is worthy of a more focused discussion and a lot of lab time. But for now, here's a basic primer on using a DMM just to take a quick voltage measurement. This is not a substitute for personal hands-on training in a safe and supportive lab environment. You must do this yourself. This is just a quick clip showing you how to apply our 4-step checklist. Function. To measure DC voltage with a DMM, put it in DC voltmeter mode. DC voltmeter mode is signified by a V with a straight line over it. AC voltmeter mode is a V with a squiggly line over it. Ignore the other functions right now. We'll get to those later. Leads. Now that you're in the right mode, check to make sure your leads are in the right place. The black lead goes in the black hole. The red lead goes in the red hole. Which red hole? If you're measuring volts, it's the red hole with a V on it. We'll get to the other plugs and modes later. Sometimes DMMs are nice enough to beep at you if you got your leads in the wrong place for the chosen function. Range. Be aware that some DMMs, like the one I'm using here, are auto-ranging, meaning that little guy inside the DMM auto-magically chooses the most appropriate range to measure your desired quantity, and some are manually ranged, meaning the big person outside, i.e. you, has to be smart enough to choose the appropriate range for the desired quantity. Let's say you're measuring an automotive battery with an expected nominal voltage of 12 volts, and you've got a choice of ranges between 0 to 2 volts, 0 to 20 volts, and 0 to 200 volts. Which range are you going to use? Obviously, the 0 to 20 volt range. 0 to 2 volts won't measure it. It's like using a slingshot and trying to kill Bigfoot with it. It's just going to piss him off. The 0 to 200 volt range will measure it, but it won't measure 12 volts accurately. It's like using a 30-06 to kill a squirrel. All you're going to get is this fine red mist where that squirrel used to be. Point is, know what you're hunting. Know its favorite foods, know its favorite watering holes, and know how to kill it in the quickest, most effective means. This is the point of these lectures. Show up prepared and your lab won't be a tedious, confusing forced march through thorn bushes. It'll be a smooth and successful hunt, and you could drive slowly around campus with yet another trophy lab tied to the roof of your car. Placement. Last but not least, where are you going to put the voltmeter? The answer is across. Voltage appears across something. Voltage is a 2-point measurement where 1 point, customarily the black lead, is the reference, i.e. the point from which all other points are compared to. If the high lead is touching something higher than the reference lead, the difference between them is positive, because your reference would have to be increased to reach the same potential. If the high lead is touching something lower than the reference lead, the difference between them is negative, because your reference would have to be decreased to reach the same potential. If we took a 2-point measurement from one side of a 12-volt battery to the other side, we would expect to see something close to 12 volts. If we flip-flop the leads where the reference was on the positive terminal and the high lead on the negative terminal, I would see the same magnitude. However, the meter indicates the high lead is actually touching something of lower potential than my reference by putting a negative sign in front of it. Realize if the battery was being measured while it was charging, we might see a higher voltage, something like 13.8 to 14.1 volts. And if the battery was discharged, we might see something like 10.6 to 11 volts. Additionally, if we measured this battery while you were trying to start the car, or drawing a substantial amount of current from it, we would see a voltage fluctuation downwards from 12 volts. This is just a glimpse of the many tentacled monster I'm desperately trying to keep a lid on. Batteries aren't perfect ideal sources, and we'll get into their non-ideal natures in later lectures. For now though, let's keep it simple. And let's say that any source I draw is an ideal voltage source. And if I say I'm using a 12 volt ideal voltage source, between its terminals, we should see a difference of approximately 12 volts. Regarding the meter, be aware that there's a limited range meters and you can safely measure. Most of the time it's written on the back of the meter or affixed to a sticker somewhere. Do not exceed this range or you'll damage the meter and yourself in the process of doing so. Certain voltage levels require appropriate levels of personal protective equipment, PPE, to measure them safely. You don't need a 40 kcal suit to measure a 3.3 volt logic circuit, and you cannot expect to survive working on transmission lines in shorts and flip-flops. Follow the appropriate company and OSHA rules and regulations, and you'll stand a strong chance of being just fine. Before we wrap up our basic electrical quantities lecture, let's introduce one more basic concept using a unit derivation example and a simple model. This concept is power, and largely the reason why we're here. Power is the consumption or generation of energy in units of joules per unit time in units of seconds. 1 joule per second is also known as a watt. Electrical power is the product of voltage across something and the current through something. The unit of volts is a measure of potential energy difference between 2 points. It's actually a derived unit where 1 volt equals 1 joule of energy per coulomb of charge. A coulomb is a means of packing up charges into more usable numbers. Kind of like a dozen eggs actually means 12 eggs. Except a coulomb is a lot more than a dozen electrons. It is a lot more. The unit of amps is a measure of the amount of moving charges in a given time period. Is also a derived unit, where 1 amp equals a quantity of 1 coulomb of charges moving by in 1 second. In terms of units, when we multiply voltage times current, what we're actually doing is multiplying a joule per coulomb times a coulomb per second. The coulombs cancel out, and we're left with units of joules per second, which again is energy per unit time, or power, where 1 joule per second is equivalent to the unit of power known as a watt. If this unit derivation exercise left you in the dust, consider the simple model I used to illustrate power. Consider a quantity of water under pressure, hooked to a water wheel. Pressure equivalent to voltage exists, but the water isn't flowing, equivalent to 0 current. The water wheel obviously won't turn. High pressure, 0 flow equals 0 power. In terms of voltage and current, high voltage times 0 current equals 0 power. Consider another case where the water is flowing but exerting no force on the paddles of the water wheel because there's no pressure. In this case, the water wheel still won't turn because the pressure or voltage is absent. Power is still 0. However, now consider a final application of this water wheel where both pressure and flow exist. In electrical terms, voltage and current exist. The flowing water under pressure exerts force on the paddle of our water wheel, and because it's moving, turns it. Power is consumed from our fluid and delivered to our output shaft. Parallels between this water wheel analogy and an electrical system exist. Power is only delivered or consumed by a system when there is both a voltage and a current. We'll return to alternate methods of power calculations in later lectures. For now, this high-level discussion should suffice. Realize these simple models, especially the water analogies I used during the course of this discussion, have their limitations. And the last thing I want you to do is cut a live electrical wire and expect to see a pool of electrons forming at your feet. These are illustrations only, and I'm urging you to move beyond these analogies as we move deeper and deeper into our discussions of basic electricity. Electricity is its own weird many-tentacled monster and must be treated as such. That being said, I admit, I sometimes use these analogies myself when I'm troubleshooting a system and I just want to get it done. Alright, that's enough for now in our basic electrical quantities lecture. Despite the fact I tried to avoid getting into obsessive technical detail, there's a lot of content in here. I recommend hitting this lecture a couple times if you're still a little shaky. Draw pictures, take notes, and for your own sake, don't leave without at least a general understanding of the basic electrical quantities of voltage, a differential across, current, a flow through, resistance and opposition, and power, the consumption or generation of energy per unit time. In conclusion, this lecture presented the basic electrical quantities of voltage, current, resistance, and power. We discussed the units to measure these quantities, common instrumentation used to measure these quantities, and the means of calculating these quantities. You should be able to pick up this concept and run with it. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech playlist for additional resources and updates.